Good day. For those of you who do not know us, we are the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we will look at the exception classes again, but now with polymorphism. In this topic, we will describe how inheritance is used in the exception classes. We will derive our own exception class from one of these classes. We will observe that our exception class is still, however, treated as if it is instances of the base class and even that base class's base class and so on. So we will subsequently therefore describe some of the features of polymorphism. All right, a recap so far. To this point, we have seen how we can extend classes with inheritance, and we can accept or modify existing functionality found in the base class, and we can introduce new functionality and new member variables in the derived classes. We looked at how this could apply to, for example, creating variations on linked lists. As well, we introduced the idea of classes to describe graphical user interfaces and saw how similar graphical interfaces or windows can more easily be described through inheritance from a base class of window, from which then dialogues and frames derive. Now, before we look at another higher level example with respect to graphical user interfaces, we will now observe some concrete examples of inheritance in the standard exception class and its derived classes. And we will note the application of another aspect of object-oriented programming, polymorphism. Now, up to this point, we have already discussed exceptions and how to throw and catch those exceptions. We have not, however, discussed their inheritance. So the base class for exceptions is the standard exception class. This is actually an abstract class, meaning that you cannot instantiate or throw a pure exception. Instead, there are two derived classes. There's the logic error class and the runtime error class. With respect to the logic error class, there are a further 4 classes that derive from the logic error class. And these include domain error, invalid arguments, length error, and out of range. There are also classes that are derived from the standard runtime error class, including range error, overflow error, and underflow error. Now you may be wondering why the initial branch into logic errors and runtime errors. Well, a logic error is an exceptional case that really shouldn't have happened because it's a case that could have been caught by the programmer. The programmer should be, for example, checking arguments to make sure that they fall within acceptable bounds. So you are not, for example, trying to access a character in a string that is beyond the end of the string, or you're accessing an array beyond the range of that array. It is assumed that if a logic error is being thrown, there's actually an issue with the source code or the design. A runtime error, however, is an exceptional case that could only be determined at runtime. And there may be various reasons for this. So, for example, the system may not have been correctly designed to handle the full possible range of possible inputs. On the other hand, perhaps an intermediate calculation causes a data type that is used to either result in an underflow or an overflow. and consequently subsequent calculations are nonsensical. Now, the default structure for almost all of these exceptions, oddly enough with the one exception being the standard exception class, is that they are all essentially a class that stores a string together with a member function what that returns that string converted to a C-style string. Now, the member function what is virtual, and it also has another modifier, no except. What this indicates is that this member function is guaranteed to not throw an exception. You can also derive another exception class from these exception classes. For example, one weakness is that the only information returned is the string. That's it. There's no other information such as what was the numeric value that caused the exception, or could there be additional information that could help deal with this exceptional case. So right now, I've created a derived class called int domain error. It's under the assumption that the domain error has to deal with an integer that is outside of the domain of this particular function. So we will now have an additional protected member variable value, and in the constructor we will assign that based on whatever was passed to the constructor. We will also override the what member function, but we will also have a value function that allows us to extract that numeric value. So here are the constructors, and note again that these constructors first call the constructor of the base class, in this case standard domain, and that is what stores the string. We then initialize the value member variable with whatever value was passed under the argument or the parameter new value. Now, when we override the what member function, what we will do is we will actually print something to the screen. We will indicate that we are logging information about the fact that we accessed the what member function, and we will specifically state that we are logging. We will print whatever the base class implementation of what is, which is just returning a string, but then we include a colon and then print out the value that is being returned. So this will be logged and can be read after the program has finished executing. However, we will still return what the parent class what member function would have returned. The member function value just returns the value that the instance was initialized with. Let's look at an implementation of a function that uses this exception class. For example, here we have a function to recursively calculate the binomial coefficients. So if n is less than 0, we throw an int domain error, and it indicates that the first argument n must be 0 or positive. The second argument is the parameter that is at issue, which is n. Next, if k is either less than 0 or k is greater than n, we'll also throw an int domain error, and again, the error message is the second argument k must be between 0 and n, and then it indicates what the current value of n is. The second argument to the constructor is the problematic argument k. Now, suppose we try to call this program that explicitly calls binomial with an invalid first argument. We're going to, of course, catch a domain error, and then we will call the what member function on it, printing whatever it prints inside of double quotes. Well, when we execute this, the exception is thrown and then caught. Now, the first statement was actually printed inside the what member function. It's logging the fact that the first argument n must be 0 or positive, and then suffixed to that is the problematic value -5. The second string that is printed is simply what is printed in the catch statement. Now, it's important to note that by default, standard cout and standard console logging, or clog, both go to the console. However, it is possible to redirect only console log files to, for example, a file that can be inspected after the fact. Now, suppose we try to run this program. What's different here is that instead of catching an int domain error, that is the class we just defined, we are catching a standard domain error. Now, you will recall that int domain error derived from standard domain error as the base class. So what that indicates is that every int domain error is a standard domain error, and thus the C++ programming language considers this instance of the class to be caught by this catch statement. So even though it's an int domain error exception, because it is a subclass of the standard domain error exception, it is caught here, and E now takes on the value of that exception. Notice, however, that when we do call what on E, you will recall that in domain error, the what member function simply returns the string, whereas in our derived class, not only does it return the string, but it also prints a logging statement. And as you can see, the logging statement does appear in the output. So even though the compiler thinks of the reference variable E as storing a reference to a domain error, when you actually call the what member function on it, it determines that that instance is actually an instance of the int domain error class and calls the appropriately overridden function for that class. Now, here once again, we are trying to catch a standard domain error, but now I'm going to print out both the result of e.what, but also the result of e.value. Now, you'll remember that the value member function is one that we added to our class int domain error. So, do you think that this will actually work? And the problem is, no, it won't work, because the compiler, as far as the compiler is concerned, the reference variable E is nothing more than a standard domain error instance. Consequently, because the standard domain error class does not have a value function, we cannot explicitly call the value member function on it, because as far as the compiler is concerned, it's an instance of a standard domain error. So if we did actually try to compile this, it would not compile. Now, in this program, we are attempting to catch a standard logic error exception. And fortunately, the binomial function will provide us with such an exception. The issue, however, is that this is still going to be an instance of the int domain error. Nevertheless, it is successfully caught, and if you look at the output, you will see that yes, indeed, it is calling the version of the .what member function that not only returns the string, but also prints an explicit statement that is meant to be saved in a log file. Now, one thing that's interesting, here we're trying to catch an instance of the standard exception class, even though we can't really create an instance of this class. Well, at least we can, but it's not ideal. So here we are throwing an exception and catching a standard exception error. Now, let's take a look at the class diagram. And yes, int domain error is derived from standard domain error, which is derived from logic error, which is derived from the standard exception class. Consequently, this will indeed catch the int domain error and will print it the appropriate messages to the screen. So here are four classes. In the left column, you can see that A is a base class. B is derived from A, C is derived from B, and D is derived from C. Now, class A has a member function A, so does B has a member function B, C has a member function C, but it also overrides member function A. Finally, class D has a member function D, but it also overrides the member function B. Now, each of these member functions will simply print to the screen that it is calling whichever class the member function is defined in and the member function name. So in class C, when we call the overridden version of function A, we say calling C :A. So here's a program where data is declared to be an instance of class D. Now, when we call little a on data, it's going to go up the hierarchy, and it will notice that the first one it finds is the implementation or the overridden version of member function A in class C. For member function little b, it's overridden in class D, so that is the one that will be called. For member function C, little c, it's defined in class C, and member function little d is defined first in class D. If, however, we initialize a reference to C with data, then we can only actually call member functions A through C, since class C has no knowledge of the member function D. However, as you can see, it still calls the most appropriate member function for an instance of class D. Specifically, it calls D double colon little b, so the overridden version of the member function B that was overridden in class D. If instead I now assign data to a reference variable of type B, once again, the most appropriate member function is called. Even though B inherits from A and knows nothing about C or D, when we call the member function little a on this reference to B, which is initialized with data, nevertheless, it will call the most appropriate member function for what the reference is actually referring to. And for data, the most appropriate call for member function little a is the one that was overridden in class C, because after all, data is an instance of class D. Same for B, we call the overridden version in class D. And finally, if you declare a reference variable to A that's initialized with data, as you can expect, if we call little a on this reference variable, we do actually get the overridden version in C, at least for data. Here's another example where we dynamically allocate memory for instances of A, B, C, and D. You will notice that the array is declared as an array of pointers to class A, the base class. However, when we actually call the member function A on each of these addresses, note that it is the most appropriate version of the member function A that is called. So specifically for class C that overrides the member function A, its version is called. Also, class D, which is derived from class C, also uses the overridden version given in class C. The instances of class A and B, however, of course, use the one that was originally defined in class A, as class A was the base class. All right, thus, the features that, first, an instance of a derived class can be assigned to a reference variable of a base class, and that the address of an instance of a derived class can be assigned to a pointer to a corresponding base class, together with the fact that you can then call a member function on such an assigned instances, that nevertheless the most appropriate member function is called, even if that member function is overridden in a class derived from the base class in question, are features of polymorphism. We saw this with the exceptions that we authored, specifically where our derived exception could nevertheless be caught by any of the base classes. Also, when the what member function was called on reference variables of those base classes, the version that we overrode in our class was still, nevertheless, the one that was called and executed. Following this topic, you have now seen how inheritance is used in the standard exception classes. you know that you can extend these exception classes to create your own, and you understand how polymorphism works with these derived classes. Here are the references, the colophon, and a disclaimer. Cheers!